Hey everybody, Samuel Singer here, the founder and executive director of Wyoming Stargazing. Thanks for joining me and welcome to Mind Bending Astronomy. In every episode, we'll share with you, a mind-bending fact about astronomy. Last time, we talked about the grand unified theory, the long-awaited theory that someday will hopefully unite the theories of gravity, quantum mechanics, special and general relativity to produce a theory of everything. One theory that can explain all the characteristics of subatomic particles, gravity, and quantum mechanics. Sounds nice, right? One of the two contenders to become the grand unified theory is called string theory. That's what we're going to talk about today. Now, string theory didn't start out as a grand unified theory hopeful. Rather, it was developed in the 1960s to understand some of the bizarre properties of mesons, which are subatomic particles that are made up of quarks and anti-quarks. Quarks are the particles that make up protons and neutrons, the building blocks of an atom's nucleus. The long story short is that when mesons were observed to interact with each other, they seemed to be connected by some invisible vibrating strings made up of the strong nuclear force. As a side note, the strong nuclear force that binds protons together and neutrons together, along with the nuclear force, that's the weak nuclear force, that's responsible for radioactive decay, the electromagnetic force, are three of the four fundamental forces that are described in the standard model of physics. That model also includes descriptions of how those forces interact with the subatomic particles that we know of. But notice, however, that gravity, the fourth fundamental force, is absent from the standard model. So, like quantum mechanics and relativity, the standard model is not a complete description of all reality. It's not a grand unified theory. So, now getting back to string theory. Before long, physicists realized that string theory, as it applied to mesons, could be modified to apply and describe the characteristics of other subatomic particles, particularly their mass. Eventually, it was realized that a formulation of string theory could potentially describe the masses and other characteristics of all subatomic particles. And that's really what lies at the heart of the current formulations of string theory. Using vibrations of unimaginably small, one-dimensional strings to describe the characteristics of subatomic particles that we already know to exist within the standard model, with their correct observed masses, while at the same time using those same strings to describe the massless quantum particles like photons and gravitons, the quantum particles of gravitation, the force of gravity. And that is where things really get messy. It turns out that to use string theory to describe both massless particles and particles with mass, the strings need to vibrate or oscillate in at least 9 spatial dimensions. That seems problematic because the universe, at least as we know it, only appears to have 3 spatial dimensions. But we'll get there. To hear a much more detailed account of the history and basics of string theory, check out the video that I have linked in the transcript of this talk. Next week, we're going to dive into some deeper details of string theory. But until then, be well, and don't forget to look up.